Hi everybody, today I want to talk about Lewis structures and how we show what molecules look like. Now, we're going to introduce Lewis structures in this video, and then in a later video we're going to kind of take them to the next step. So let's go ahead and get started. Just so you know, some key terms you need to be on the watch out for. Of course, Lewis structure is one of them. Something called the duet rule, the octet rule, bonding pair, lone pair, single bond, double bond, triple bond, and resonance. These are some words over the next couple of videos that we're going to kind of highlight. So the ones we're talking about today are Lewis structure, duet rule, octet rule, bonding pair, and lone pair. The others we're going to save for another video. Now, a Lewis structure is a representation of a molecule that shows how the valence electrons are arranged among the atom. Now, this is particularly important because we're talking about how the valence electrons are arranged. Valence electrons are responsible for bonding. Okay? So when we talk about a chemical molecule or a reaction, we say that the valence electrons are the ones involved. Now remember, valence electrons are the highest energy electrons in an atom. Okay, so if we look at the electron configuration for calcium, which I have here, this is the long-hanging configuration for calcium, but we're only worried about the highest energy ones, which 4s2 is the highest, okay, because 4 is the greatest number there. So these are my valence electrons. And in fact, because I have a 2 right there, that means I have 2 valence electrons. Okay? Now, if we look at the shorthand configuration, remember that the first part of the configuration up to the P6 represents a noble gas. In this case, it represents argon, which is the noble gas right before calcium. So what's left are the valence electrons. Notice these are the same. So a noble gas configuration shows you the valence electrons, which is very important. Now over here to this little dot thing. This is called a Lewis structure, named after Gilbert Lewis. Okay? Now a Lewis structure uses dots to represent the valence electrons. Now, since calcium has 2 valence electrons, it gets 2 dots. Okay? And I want you to imagine that there's a box around calcium. And this will make more sense later on. But basically, according to our electron configuration rules, we put the dots by themselves before we start to pair them up. And like I said, that'll make more sense here in a second. Okay? And I want to reiterate, we only show the valence electrons when it comes to Lewis structures. Now, here are 2 special Lewis structures that kind of lead into what we're going to talk about today. Potassium has the valence, has the electron configuration argon 4s1. Which means it should have 1 valence electron. Oh, sorry. Now, bromine over here has the shorthand configuration of argon 4s2, 3d10, 4p5. So if we look at just the highest energy sublevel, it has 7 valence electrons. Oh, that's not right. Valence electrons. So its Lewis structure looks like this. 1, 2, 3, 4. Now we start doubling them up. 5, oh fudge, 6, 7. Okay, so that's the Lewis structure for bromine. But here's the thing I want you to know. When atoms bond, what they're trying to do is either get rid of those valence electrons or accept valence electrons so that they look like a noble gas. So in this case, potassium only has one valence electron. So it's going to lose that electron somewhere. I'm just going to draw an arrow showing it that it's lost to something, which gives me calcium plus 1, or 1 plus. Now we've essentially gotten rid of that valence electron, and we're left with the argon configuration, which is very energetically stable. Energetically stable. Now bromine is the other way. Bromine is very close to filling up or looking like a noble gas. It's only one element away from a noble gas. So it's going to gain an electron from somewhere so that its new configuration turns out to be P6, which gives it a negative or 1 negative charge. But now you'll notice it has 8 valence electrons, so it looks like the nearest noble gas, which is krypton, which is also energetically stable. So we use these Lewis structures to demonstrate or model that the atom wants to either lose or gain electrons in order to become energetically stable. Now, metals typically lose valence electrons because they're closer to losing and getting 8 valence electrons, whereas nonmetals typically gain because they're closer to noble gases if they gain. Now, there are 2 rules that say whether or not an atom is going to, or how many an atom is going to gain or lose. Hydrogen follows the duet rule. Duet, of course, stands for 2. What that means is hydrogen wants 2 valence electrons. Oh, fudge. Valence electrons. Now, hydrogen already has 1, as we can see in the Lewis structure. But when they come together, now they're sharing 2. 2. I'm going to abbreviate valence electrons VE. So now it's sharing 2 valence electrons, which makes it energetically stable. And if we look at the orbital diagram, this kind of makes sense. We have 1s1, 1s1, okay? And they're going to come together to form H2. So now it's configuration where they're sharing or overlapping those valence electrons now looks like helium. Hydrogen is one of the very few elements that follows the duet rule. We're not going to really get into the other ones, okay, because it wants to look like helium. Okay, hopefully that makes a little sense. All other elements follow what is called the octet rule. With the octet rule, elements want 8 valence electrons. If we look here at fluorine, it has 7 valence electrons. Okay? And the same is true for this fluorine over here. So what's going to happen is these 2 fluorines are going to come together and they're going to share this valence electron. And another way to show this would be to show that the electron clouds are overlapping, okay, so that they're shared. In this way, it quote-unquote looks like each element has 8 valence electrons because octet stands for 8, and 8 valence electrons are stable. Well, are more stable. Let's say that. Are more stable. And the whole universe seeks to be stable. Now, this bonded pair right there is called a shared pair. Sometimes it's also referred to as a bonding pair, which is what we'll refer to it as, a bonding pair of electrons, because that's where the chemical bond forms. These electrons on the outside, let me draw this over here, are called lone pairs. They are what the element brings to the party, but are not involved in the bond. Okay. Now, noble gases do not share electrons because they already have a full valence shell, and since they have a full valence shell, they are energetically stable, which is why they are non-reactive. Why do I feel like I spelled that wrong? You know, if I spelled it wrong, don't hate me. Nope, I had it right the first time. Energetically stable. Okay, notice that each valence electron, or each noble gas, already has 8 valence electrons. Since they already have 8, that means their electron shell is full. They have Ns2 NP6, where that N is whatever row they happen to be in. Okay, they're already stable. They already have 8 valence electrons. And that's what everything wants to look like. Every element wants to have 8 valence electrons. Now, I would be remiss in my duties if I didn't bring up the fact that helium has 2 valence electrons. Remember, it follows the duet rule, not the octet rule. Now, we have seen Lewis structures for just individual atoms. However, we definitely want to look at how we show valence electrons for molecules. The next slide is going to have a lot of text on it. Okay, I'm going to read the text, but then we're going to practice the text. Okay? Now, in order to draw the Lewis structure for an element, for a molecule, you draw what's called a skeleton structure with the biggest or least electronegative atom in the middle and the others on the outside. Then we have to count the total number of valence electrons. Then we connect the outer atoms to the inner atom with a single bond. Then we place the electrons on the outside atoms. Then we place all the remaining electrons on the central atom. Okay? So, let's write the Lewis structure for water. Okay? Remember, the formula for water is H2O. Okay? Now, our first step, of course, is to draw the skeleton structure. Okay? With the biggest or least electronegative atom in the center. In this case, oxygen is the biggest. So it gets put in the center, and hydrogen gets put around it. Okay? Now we're going to count the valence electrons. Hydrogen is in the first column, so it has 1 valence electron. And there are 2 of them. Oxygen has 6 valence electrons. And there's only 1 of them. And I know oxygen has 6 valence electrons because it's in column 16. Okay, it's in the 2p4, or it's in the p4 column. So I know that the S is full with 2, and then of course it has 4p electrons, which add up to 6. So this means that my final structure will have 8 dots on it. Now I connect the outer atoms to the inner atoms with a single bond, which is 2 dots. Okay, so I have used 4 bonding pair electrons. And I have 4 electrons left over to account for. Now the next step is to place all electrons on the outside atom, okay, in order to complete their octet. But hydrogen only needs 2, and that's something we need to remember. Hydrogen only needs 2 valence electrons. So the hydrogens are complete, which takes me to step 5, which is place all remaining electrons on the central atom. Since I have 4 left over, they go on the central atom, and those are lone pairs. 4 lone pair electrons means I have none left over, and if I count my valence electrons, 2, 4, 6, 8, I have enough the way I should. Okay, and oxygen looks like it has 8 valence electrons. Hydrogen, each hydrogen looks like it has 2 valence electrons, which is what it should look like. Okay, so we're good there. Now for HCl, first we draw the skeleton structure. Since there are just 2 elements here, we just draw them side by side. I count my valence electrons. Hydrogen, has 1 valence electron, and there's only 1 hydrogen in the formula, so that's 1. Gosh darn it. Chlorine, because it's a halogen, has 7 valence electrons. I know this because it's in column 17, or the P6 or the P5 column. There's only 1 of those. So altogether, I should have 8 valence electrons on my final structure. Now I connect the outer atom to the inner atom with a bonding pair. Okay, so that takes up 2 for my bonding pair electrons. I have 6 left. Now they never go on hydrogen. Okay, hydrogen does not get an octet. Hydrogen has a duet, so those extra electrons are going to go on chlorine. 1, 2, 3, 4, 5, 6. 6 lone pair electrons. I have no valence electrons left over. And that looks good. I want to reiterate, hydrogen never has more than 2 electrons. Okay, please keep that in mind. It is very important, because I can guarantee somebody is going to mess that up. Now, here's a more complicated one. We draw the Lewis structure for NCl3. So we draw our skeleton structure first, which is where we put nitrogen, because it's the first one and it's the least electronegative, in the center. Okay, we put the chlorines around it. Okay, it doesn't matter where you put them. We're kind of trying to box nitrogen in. So now we count the valence electrons. Okay, nitrogen has 5 valence electrons, and there's 1 of them, which comes up to 5. Chlorine has 7 valence electrons, but there are 3 of them, which means our 7 times 3 is 21, which means our final structure should have 26 valence electrons. Now, our next step is to connect the outer atoms to the inner atoms with bonding pair electrons. Now that took up 6 bonding pair electrons, so 6 bonding pair electrons, which leaves me 20 left over. Now I complete the octet on the outer atoms, which in this case comes out to be, each chlorine already has 2 from the bonding pair. So now I just have to add the other 6. Okay, so 2, 4, 6, 8. And each chlorine looks the same. Okay, now that total took up 18 valence electrons. So minus 18 lone pair electrons, which leaves me 2 left over. And my last step for now is that those extra 2 go into or go on nitrogen. Okay? Which makes sense because right now nitrogen doesn't have an octet. Since it doesn't have an octet, it has to get those 2 extra electrons from somewhere, but fortunately I already have 2 valence electrons left over, so I just put those on the top, and there we go. So if we double check ourselves, we notice chlorine has 8. Each chlorine is looking like it has 8 valence electrons, which it wants, and nitrogen looks like it has 8 valence electrons, okay? Which makes this a complete and correct Lewis structure. Now, if you have any questions or comments, please leave them below or feel free to email me and we will work them out.